The Sun is a sphere of plasma held in a delicate equilibrium between the inward crush of gravity and the outward pressure of nuclear fusion. This balance provides the specific thermal energy required to sustain liquid water on our planet. This engine has been running for 10 billion years, but it is a finite system. Eventually, the hydrogen fuel at its core will be exhausted. Pop culture often depicts this end as a sudden, violent supernova, a singular explosion that instantly vaporizes everything in the solar system. While a rapid detonation is a common cinematic trope, the physical reality of stellar death follows a much longer and more complex timeline. Because of the 150 million kilometers separating us from the Sun, there's a delay in how we perceive changes. If it exploded right now, the information travels at light speed, meaning life on Earth continues normally for exactly 8 minutes. There would be no seismic warnings, no shifts in the sky, and no physical precursors to signal the end of the solar system during that window. We are so far away that we would remain completely oblivious until the very moment the light from the explosion finally reached our atmosphere. At minute 9, the thermal wave hits. The side of the Earth facing the Sun is exposed to a direct blast of radiation so intense that the surface boils away instantly. On the other side of the planet, the atmosphere would trap the surging energy, causing temperatures to spike to 15 times the current heat of the Sun's surface. Beyond the heat, we lose the gravitational anchor. The Sun's mass is the only force keeping Earth on its orbital path. Once that mass is gone, Earth's orbit breaks, traveling in a straight path out of the solar system into the interstellar void. This hypothetical scenario destroys the planet through two distinct failures: a catastrophic thermal surge, followed by the total collapse of our orbital mechanics. Survival would require moving deep into the crust. A few meters below the surface, the Earth maintains a natural internal temperature of 17 degrees Celsius, which could provide a temporary refuge from the chaos above. However, without solar input, the surface temperature would drop to minus 18 degrees Celsius within a single week. Within a year, the global temperature would reach minus 73 degrees. At this point, the oceans freeze from the top down, creating a thick crust of ice over the world's water supplies. After 1,000 years of drifting in the dark, the temperature would become so low that the atmosphere itself would freeze and collapse onto the surface as solid waste. This collapse would leave any subterranean survivors defenseless against constant cosmic radiation and meteor impacts that were previously blocked by the air. Earth's internal heat acts only as a finite battery. Without the Sun, that energy eventually dissipates until the planet reaches thermodynamic equilibrium with the freezing void. Fortunately, the supernova scenario is physically impossible for our star. The Sun lacks the necessary mass to trigger that type of explosive collapse. 5 billion years from now, our Sun will run out of hydrogen and swell into a massive red giant. After expanding, it sheds its outer layers and shrinks into a white dwarf, a small, dense core cooling over trillions of years. The actual threat to Earth is this gradual expansion, which will eventually engulf the inner planets as the star's outer atmosphere reaches out toward our orbit. In astrophysics, the death of a star isn't a terminal event, but a distribution system for the galaxy. As the Sun expands and loses its outer layers, it ejects the heavier elements forged in its core out into the surrounding cosmos. These remnants become the raw building blocks for future nebulae, which eventually collapse under their own gravity to form new stars and planetary systems. The eventual dissipation of our solar system is the process that allows these materials to be recycled, providing the necessary ingredients for new structures to form across the galaxy.